We know that the 4 stages of crystallography is protein expression, purification, crystallization, crystal growth, harvesting the crystals and diffracting the crystals, as well as building, solving, and refining the molecular models. This is very important for therapeutic drug discovery because if you solve co-crystals of proteins and their complexes, or proteins and nucleic acid complexes, or proteins and inhibitors, you can design these therapeutic treatments and ultimately target and treat diseases such as cancer. Our focus for this specific video is understanding how do you get from diffraction data, or the spots, to our molecular model. At a synchrotron, the diffraction data can be automatically integrated, indexed, scaled, and integrated into an electron density map, which is the blue mesh over here. But they don't have a model. So you only have the electron density map, but you don't have a model. So what you do now, you have to build and solve the model by creating a model and then fitting it in as best as you can into the electron density map. So how do you do that? When you first do PHENIX Autobuild, or essentially build your model from scratch, you need to have your reflection file, or essentially all of your electron density map data, also your sequence file, or like your amino acid sequence. With this information, PHENIX Autobuild can go in, create your amino acids for you to match it up with the reflection file data. PHENIX Autobuild will create a PDB structure file. And then you take your PDB structure file, you take your reflections file, you take your sequence file, and then you plug it into PHENIX.refine. And then with PHENIX.refine, you'll also get a now refined PDB structure, and then also the same MTZ file. How do we get the MTZ file? How do we get the sequence file? That is what we're going to do today. So we're just going to go ahead and go over here. There's a PDB, go into the PDB, and then essentially what you're going to do is search 7OL6. 7OL6 is a lysozyme protein with small molecules known as imidazole. Imidazole is just like the histidine amino acid without the carbon backbone on it, and imidazole is a good inhibitor of lysozyme. So this is a very good test case scenario to see how do you solve a structure with inhibitors in it. So 7OL6, right? Okay, so it was deposited, or it got released onto the PDB in 2021. Method was X-ray diffraction. Resolution was 1.1 angstroms, very high resolution. Wow. So there are free values 0.16, and there are work values 0.147. Wow, guys, that is very good. So generally, after you get your diffraction data, you have to refine it. Generally speaking, your refinement will create an R value free and R value work of around 0.2-ish. If your resolution is stronger or higher resolution than 2 angstroms, say for example 1.5 angstroms, then your R free and R work should be around 10% of that, so basically 0.15 or less. If your resolution is like 1.1 angstroms, then ideally your R free and R work should be 0.11 or less. But of course, getting to 0.15 or 0.116 is very difficult. And so generally, if you are below 0.2, or in this case 0.16 or 0.14, that is already very good. So we need 2 things, the sequence file and the actual experimental data. How do we do that? You go to download files. So FASTA sequence is your sequence information, so your list of amino acids. And then map coefficients, your MTZ file, is your experimental data. So what you're going to do is you're just going to click this to download it. All right. And then you click this to download that. Okay, so now those 2 are downloaded. Before we do anything though, we first have to go to downloads. Okay, we first have to go and bash into here. So bash into your downloads folder. Okay, PHENIX is interesting because you need to have a dedicated folder for your project for PHENIX to run in, where the PHENIX program accesses its files and then produces its file outputs. So what we have to do first is you go to your root directory, cd into PHENIX, your PHENIX folder, right? Okay, cd PHENIX projects. Okay, and then you go into your PHENIX folder. Right now I already have a lot of folders. I want to make a directory or make a folder. I'll just call it 706. Okay, so this is going to make a new folder. I'm going to go into my 706 folder now. So yeah, there's nothing in my folder because I just made it. And you just do pwd to print your directory, and then we're just going to go back to this downloads folder. So I'm just going to go back to the downloads folder by bashing into it. Okay, so we're going to pwd this. I don't know, we might not have to pwd that, but cd into my PHENIX projects, and then 7OL6 folder, and pwd this. Okay, so now we just have to go back to downloads, and then find our, okay, so didn't like it when there's a space, so you have to put quotation marks in it. Okay, so now you have to find your stuff. So it is copy, so cp 7OL6 underscore phases dot mtz is your mtz file. Because we're already in the downloads folder, we don't have to specify the location of the item that we're trying to copy. If you're not in your downloads folder, then you have to specify the directory, but if you're already in the downloads folder, then it's okay. And then you just copy the final destination, and then you paste and you enter. Okay, so that's good. Then you copy the other file, which is your sequence file. You also paste your location, destination. Okay, cool. Now we're going to cd into here. Okay, and then now ls, and hooray, it's there. So one thing is sometimes PHENIX does not like to use FASTA files. So what are you going to do? Sometimes they like to use .seq files or .dat files. So we're going to try .dat files this time. So you're just going to nano. All you have to do is convert this FASTA sequence into a .dat file. So you nano and then you rcsb underscore pdb. And then because this is the only file in here that has the same, so you just tab autofill. Okay, so now you're here. The FASTA sequence, FASTA file has some general information like where did the protein come from, what is the specific information. We don't need all this other stuff. We only need the actual sequence. So I'm just going to go in here. I'm just going to click backspace, or so backspace didn't work. I'm just going to click delete, highlight, delete. Okay, so just delete, slow down at the end. Okay, cool. Now we see this asterisk saying that, hey, you modified this. So we're just going to write out. So press Control O. Okay, file name to write. We're going to turn this into not FASTA, but .dat. And then we're going to say enter and say save under a different name and then shift yes. Okay, so now we see that the new file has been created and it's a .dat file and it's just the sequence, Okay, now we say Control X to exit, Control X. Okay, so now if we do ls, hooray, it is mtz file, the FASTA file, and then the .dat file. All right, now we are ready to do PHENIX Autobuild. So we can just cancel out of this. So we navigate right to cd PHENIX, or let's ls. cd into your PHENIX folder, PHENIX 1.21.5207, and then no, cd PHENIX 1.21.5207. Okay, ls, and then you're going to say source PHENIX sh. Okay, and now I can say PHENIX. Okay, that's cool. Okay, cool. So I don't know what this folder is right now, but this is the folder that PHENIX is currently in. We don't want to have that folder. We want to go to the folder that we just created. So if I go into PHENIX projects, the folder that I just created is called 7OL6. Okay, this folder is going to have my MPZ file, my 2 sequence files. Okay, we're going to use our .dat file. So this is going to be the directory that we tell PHENIX, hey, I want you to work in this folder. This is the folder that I have all the information in. Please stay in this folder. So you click open. So now you see that PHENIX is now in this folder. We're going to say new project in this folder, 7OL6, okay? And project directory, and this is just a general folder. I don't like that folder. I want to go to the folder that I just specified, which is this one. So click open. Okay, this is the correct folder now. Okay, cool. Okay, so now we see a check mark in our new project, okay? And first things first for our brand new project. So if we say job history, nothing in the job history because it's a brand new project. So model building, check marked on our new project. We're going to go to model building, Autobuild. It's going to take your sequence file, going to take your phase information, your MPZ file, and create a brand new structure out of scratch. So you go into Autobuild. Oh, okay. We're just going to add your files, which is mtz and your .dat file. Okay, cool. So initial maps, so they guessed correctly that .dat is your sequence. MTZ is your initial map, yes. But it's also your experimental data. Okay. Now, okay, so this is correct. Yeah, this is all correct. So you have your sequence file, and your experimental data, phases, right? So if you don't have your phases, it'll be very hard to create your model. So now see other options, space group. Okay, so we're going to just make it simple here and just say max iterative build cycles of, let's just say 3 and 7. Okay, build outside the model, we can just leave that checked. Righty? And since everything is looking good, actually no, let's just change this to 1. If you do 1, then this process takes just around like 30 minutes or so. Okay, so we'll click run. Now it's running. Sometimes takes a long time. I'm going to just directly use the structure that I had previously built using PHENIX Autobuild. So I go back to my project folder. Okay, so you see that when we change projects, the directory also changes. So we change back to the correct project folder. And now instead of going to model build, we're going to go into refinement. So now we already have a structure that was built using auto build. We're just going to refinement or make it better. So PHENIX refine. Make sure your project is selected, go into PHENIX refine, and then all you're going to do is you're going to take the copied structures that you copied into your folder. You add your file, which is specifically overall best PDB. This is going to be the PDB structure that PHENIX Autobuild automatically created for you. So you take that overall best refined data.mtz. This is the mtz file, which is basically the same as a raw file. So you can just directly use that, and you can also use the .dat file. Okay, plug that in. So input model, very clear. X-ray data with the X-ray are free flags, which is important. Sequence file, so they got it all correct. Refinement, output, amber. Oh, so we go to refinement settings. Looks all very normal. We can just go ahead and run locally. And here we go. Coot is opening because as it's refining the data, Coot can show you, hey, how does the data look so far? There we go. Something that's happening. Okay, so right now we see our R work and R free are very high. This is not good. Ideally, your R work and R free should always be below 0.2. And seeing that the resolution for the electron density map was 1.1, right? Resolution was literally 1.1. So your R work and R free should ideally be less than 0.11. Of course, that's not always really possible, as evidence in the PDB structure where their R work and R free was around 0.14 and 0.16. But those two, 0.14 and 0.16, are definitely way lower than 0.28 and 0.27. So our goal through refinement and Coot refinement, and then go back to PHENIX refinement, Coot refinement, is to decrease the R work and the R free until it's as low as possible. In this case, so that it matches what was deposited in the PDB, which was 0.14 and 0.16. Okay, so our work now decreased dramatically to around 0.21. That is good. But we have to do more refinement through PHENIX refine and Coot to get that as low as possible. Our clash score is 2.7, which is actually pretty good because your clash score definitely should be less than 20. So seeing that our clash score is only 2.7 is pretty good. Right, so it is now finished. So you can see the blue areas, the blue mesh is electron density map, our MTZ file, and inside of the mesh is the structure that we're trying to build and refine to match the electron density. The green areas are pockets where there's electron density where it can't be really explained, and the red is where there's like a model or maybe waters that do not have electron density to explain it. If it's like tiny red and green spots, then it might not matter all that much. But if it's a major blob or it's a major density of incorrect density or density that's not explained, then that's definitely something that has to be investigated into. So run status, this is good. Log output, well, this is finished. This is very good. Sequence check. Let's see. So sequence check. I'm gonna check my sequence. This essentially is going to tell us how the sequence is. So the PDB and the sequence. The sequence is the sequence that we gave the program, or the DAT file, the .dat file, that was the sequence we gave them. So all the sequence, they are all exactly correct, right? Except for this first one that was not explained. All of these are all correct. Okay, cool. So all of the amino acids were put into place correctly, except for the first amino acid and the last 3 amino acids. That's cool. That means when we go into Coot and try to solve or further refine the structure, we only need to add in this first amino acid and add in the last 3 amino acids, and then just adjust the positioning of the amino acids. We don't have to mutate or change any of the amino acids in the structure because it is all correct. So that is good. Now what we're going to do is going to Coot. So for example, if we have run status or this mole probity, this is going to tell you any clashes that we have. So most of these clashes are just water, which isn't all too concerning. So 3 things when you get your PHENIX.refine results and want to plug them into Coot to make them even better. First is make sure all of your amino acids are correct. And in this case, yes, they are, except for the first one and the last 3. And then the second is make sure all of your amino acid residues fit into their electron density as correctly as possible. And what I mean by that, adjusting the amino acids, seeing if the amino acids have any issues, seeing if they could be better fit into the electron density. And the third is filling in any of the missing ions or missing small molecules, which in this case is for the most part imidazole. After that's all finished, we can plug it back into PHENIX. So first and foremost, we can just take a look at this. All of these like little waters that are being annoying. Yeah, we can go ahead and get rid of some of the waters if the program doesn't like it. Okay, so essentially how to get rid of the waters is what we do. We click delete, then we say water, then we say click, and the water is gone, right? And then we go to next water. Okay, why am I deleting this? Because it's there, it's red, so there's red mesh saying like, hey, this doesn't belong here. There's nothing to explain this presence, and it's also making PHENIX angry. So that is why we are. So this is an interesting looking blob. So if we look closely, right, if we click on this, it'll tell us, we're supposed to tell us, oh, there we go. This is the second amino acid residue. So if we try to find our first amino acid residue, it only starts with the second, and that is this one. And then we have this big blob of electron density over here that cannot be explained. And we're like, wait a second, sequence check. Where's our sequence? First one was lysine. So what do we think? This probably is a lysine. How do we fix this? Add a terminal residue. So we take this, click on that. Okay, boom. This is now a lysine. We can just click shift space to go up. Okay, this is lysine. But no, the computer's like, no, I don't want it to be a lysine. I want it to be an alanine. Well, we know that that is not correct. So we're going to go and mutate this. So mutate and autofit. Click on this and say, hey, I don't want alanine. I want lysine. So lysine is K. Okay, cool. So do we think this is correct? First, we want to make sure we are on sigma 1, which is just about 1 angstrom or so. Okay, so sigma 1, we can't really see anything, so we're just gonna slowly scroll up until we start seeing hints of things. Okay, let me just turn off this green thing. I cannot see. Okay, cool. So we started seeing hints. 1 hint, 2 hint, 3 hint, and then more hints over there. Okay, so do we think this current position is correct? Maybe not. So what we're going to do is we're going to click this, move it. I mean, yeah, but not, yeah. Let me just move this over here. Oh no. Okay, let me just move this over here. How's that? I think this should go over here, you know? You know what I mean? Okay, let's scroll up. No. I'm gonna scroll this over here. I'm gonna scroll this over here. No, doesn't want to go in there. Okay, I think we'll just accept that for now. It looks moderately fine. At least the atoms seem to be lining up correctly for the most part. For the most part, that is okay for now. Okay, let's turn on this density back. See what I mean? Density is going in the other direction, which is exceedingly strange. Just click this again. Let me move this down. Yeah, it doesn't like to do that. Okay. So we're just gonna keep it that way. Okay, cool. So now if we go here, we're like, okay, chain A. Wow, we see lysine now. This is lysine. That is good. Okay, so that means when we do PHENIX.refine again, next time it comes along, PDB, our structure is gonna say lysine right here. So if we go to the very end, we have 3 amino acids that are missing. Let's go to the very end. Okay, glycine, apply. Okay, cool. Now we are here at glycine. I can't see everything, so I'm going to control right click and make this like this so I can see more things around here. So here's glycine. Let's shift up. Okay, so this is isoleucine. Then click on spacebar. We now shift to arginine, which is this guy. Now click spacebar again, and we're shifting to glycine, which only has 2 hydrogens. And then supposedly after glycine, it's supposed to be cysteine. So what do cysteines like to do? They like to form disulfide bridges. What's a disulfide bridge? Tertiary structure. Disulfide bridges are essentially covalent linkages that connect protein subunits or keep the protein together. Okay, so let's just scroll back to 1 angstrom. Now I can see everything. This is good. So what is this actually? Oh, it's another cysteine. I'm just double clicking. This bright yellow over here, let me just turn off this. You can see this bright yellow over here is a sulfur. Why? Because cysteine is just like, nitrogen, carbon, and then the N-C alpha C prime going in this direction. But cysteine has carbon and then a sulfur. And what you usually see is a bridge. So for example, if we actually just go to any other sulfur group, just go to any other sulfur group, cysteine group, for example, let's just go to here. Okay, what do we see? We see here's one cysteine, and then there's a sulfur coming off, and then here's another sulfur, and then here is that other cysteine. So it's cysteine 64 is connected in a disulfide bridge with cysteine 80. Okay, let's go to another cysteine. Let's find another cysteine. Okay, cysteine number 6. Oh, cysteine number 6 is now the one that we have to fix. Okay, so we have cysteine number 6. Let's turn our displays back on. Okay, so what to do? Sulfur is really interesting because sulfur has a lot of electron density. Seeing that that is the case, and seeing that sulfur disulfide bridges are 2 sulfurs connected together, this water molecule that's here as a placeholder most likely does not belong there. So we're just going to delete this. Okay, now we are going to add in a cysteine residue. How are we going to do that? This right here, what is this guy? This guy is your glycine. So the last residue right before that expected cysteine residue. So we know that we have to add a terminal residue because it has to go somewhere, right? But also, it needs to go in this direction because this is where the disulfide bond is happening. All you have to do is add terminal residue. So you click on this. Okay, is that the correct residue? Does it even fit with electron density? I don't think so. What is this residue that they just randomly added? Alanine. Well, we don't want alanine. Because guess what? If you turn on this display, it is not matching up with electron density. So we are just going to go back over here and mutate this. Okay, mutate this into, what is it? A cysteine. So is that correct? The sulfur is pointing in this direction, and the next carbonyl is pointing in this direction. Is that correct? How do we make this disulfide bond? The 2 cysteine, the 2 sulfurs have to be connected. Okay, so what we're going to do is, let's see if we can make this work. No, that didn't work. We're going to use real space refine. Okay, obviously did not work. So we're going to snag the sulfur and move it over here. Okay, well, I didn't want to move. We're going to snag this oxygen and move it over here. Now sulfur jumped over there. Close, but not close enough. There we go. Now that is correct. Okay, so what if I did this? No, it isn't like that. Oh, that's interesting. Okay, Alexis, I better. Okay. Now that is our disulfide bridge. So that is good. Okay, we still need 2 more residues. So for example, if we check the alignment, right, we plugged in the lysine, so that's good. We also plugged in the cysteine, so that's good. Now I just need to plug in the arginine and the leucine. Okay. Add terminal residue. Click. Okay, so it was obvious that the other one was better, so I'm going to flip this. Now I'm going to real space refine this. I want to move this around to this side. Okay, maybe we put in the side chains. Okay, we're gonna let PHENIX refine fix that. So we did the first thing, which was plug in all of the amino acid residues. That is good. Now, another thing that we can do is real space refine everything. Usually when you're trying to fix something, for example, go to this chain, go to lysine, cool, let's go to lysine. If you're here, right, and you're like, I want to make lysine as best as I can possibly make it, I'm gonna click here and click here. Okay, it's already good. And then you can press space bar and then click on the next one. For example, this this guy, this valine. Okay, it shifted a little bit. Right, the thing is, you can do larger stretches of refinement. at the same time. Right, so you can just click and then click, 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 and then, oh no, and then click that. Or if you think that was too broad, you can still go back and then real space refine them, maybe like amino acids 2 by 2. The idea is you can do multiple at the same time. Yeah, we see that, this is a good cysteine. So just move along, right? This is alanine, and just move along, just making sure that everything's looking good, which it is. Okay, we accept because it's all green. Just continue moving along. Okay, so this guy, and let's just do that guy. Okay, so as we're moving along, you can see that you're traveling towards the N terminus to the C terminus. So N, C alpha, C prime, N, C alpha, C prime. So each place that Coot brings you to is the next C, or C alpha, the chiral carbon that has the side chain. So this one, the side chain is right here, you see. So yeah, what I wanted to show you guys was there's probably one way you can just do all of the amino acids at the same time. So you can go back to lysine. Okay, and you just click this one side, and then you go all the way down to leucine, and you just click the other side. And then it'll just do everything for you. Okay, so we accept that. So if you take a look at, for example, let's just go to the middle, like asparagine. Okay. If we do real space refine along this area, it's already completely real space refined. We plugged in the amino acids. We did real space refine for all of the amino acids. Now the last thing is plugging in the histidines. So validate, density fit. See that these are very red, which is very bad. That's okay. We're going to gradually decrease these over time. All these last couple ones are waters. So waters are used as placeholders for basically anything. So even if there's nothing there, PHENIX might just plop a water right in there. Even if there's just absolutely nothing there, they'll just put a random water right there. So what do you have to do for these waters? You have to check the waters to make sure there's none of your small molecules that got place held as a water. What's a small molecule in this scenario? Imidazole. So we talk a lot about proteins, and if you just co-crystallize a protein with an inhibitor, then you can inhibit the protein, which could be useful for anti-cancer research. So now we have this protein, which is lysozyme, and then the inhibitor for this protein, which is imidazole. And we can see in real time what it's like to term the structure of the protein along with your small molecule inhibitor. So we move over here, continue moving along. Okay, here's one. You're like, that is an interesting ring-shaped situation here. Why would water be like that? Precisely, water would not be like this. So what is this? We know that our inhibitor molecule is called imidazole. What does imidazole look like? It's a 5-membered ring with 2 nitrogens and 3 carbons. So this is a 5-membered ring. Let's just go ahead and delete these placeholder waters. We do not need the placeholder waters. Okay, we want Coot to plug in an imidazole compound. How do we do that? So we just say edit, we go to modeling, add other solvent molecules. So all you have to do is add new residue type, IMD, and click add. You have imidazole. Okay, it's going to do a jiggle fit, and it's done. Like, well, that was quick. Let's just refine this just in case. Yep, that is correct. So what is this imidazole actually doing? Oh, that's a good question. Let's find out. We can see measure environment distances. Show residue environment, yes. Okay, so it's interacting with the water. This nitrogen might be forming a hydrogen bond with this nitrogen and its hydrogen. Maybe there might be a little bit of pi stacking going on here. Seeing the binding pocket and the small molecule inhibitor in PyMol will be very useful to see how the inhibitor is binding in the binding pocket. Okay, so we were only able to capture one of the imidazoles, but there's actually 4 or 5. But that's okay, we can save that for after another round of PHENIX refine. So now what? File, and then we say save coordinates. Okay, select file name. Going to go back into our project. Right, you guys will just have .dat, .mtz, and .pdb. So we're just going to call this, let's call this. Let's call this, refine one Coot. 1. Okay, because we went through PHENIX.refine the first time, and this was the Coot the first time. Okay, and save as PDB is save. Okay, cool. We're back in this project. We're gonna do another PHENIX.refine. Add file. So we're in the correct project folder. Yes, that's correct. Coot. MTZ. And let's see. Fasta. No, dat. Okay. So yeah, sequence input model, because we just refined it. This is Coot 1 out of refine 1. Okay, refine settings, looks good. Okay, run. Clash score 2.5, that's better than 2.7. You see these yellow ones? Those are disulfide bonds. So it's connected. This one is actually methionine because it also has carbon on the other side. It's now finished. So, first thing, are all the amino acids still there? Yes. All the amino acids are now there. That's good. Second part is real space refined. Let's do that super duper quick. Chain A, as design, apply. Okay, let's just go in here, real space refine, click this, then go to the very end. Okay, and then click that again. Alrighty. This model was output model of the second PHENIX refine. Say, for example, you take this, you refine it some more, put it back into PHENIX refine, and take it again in Coot, and then put it back into PHENIX refine, and take it into Coot, and put it back into PHENIX refine, and then you get a really good refined model. Say, for example, I don't know, at least 0.16 or 0.17 are free R work. And you're like, okay, I'm ready. I want to see how well I did. And you're like, okay, I want to check to make sure if my model matches up with what these scientists had published and put onto the PDB. You just say file, save coordinates. We're just going to call this refine to Coot 2. Say, for example, you're like, yes, I did refine 10, Coot 10, and I'm very confident about this. You save, and then you open PyMol. And then what you do is you file, open, and then you go to Ubuntu. You can say home. Okay, go to PHENIX projects, go into your project, and now you have refine to Coot 2. Okay, all of those pluses are water molecules, and that's the one imidazole that we were able to find. We're going to fetch 7-OL6, which is the original structure. Okay, well, those are separated, so what we're going to do is we're going to take our Coot 1. So if we go to our Coot, we want to see them overlapped to see how well does our refined one compare to the original. So we're going to say, we're going to say align to 7-OL6. Now we're going to go to the 7-OL6, orient here. Okay, we're going to select, okay, it is actually pretty good. Okay, it's just, this last bit is not quite correct. Besides that, everything else looks okay on the macro scale. For example, if we hide this, right, you're like, okay, that imidazole we put, it was correct. But what this has is the magnesium ion and also a sodium ion and a chloride ion. So we have to go back and figure out how to add those in. And then also, if we just say show sticks, hide ribbon, or hide cartoon. Okay, then we'll see everything a little bit more clearly, right? This is show surface. Okay, so this little guy is in this binding pocket. That is very interesting. But yeah. One thing that is not matching up is this side, which makes sense. And also that is also not matching up. This is not matching, this is not matching. So the game is to check yourself, see how well you're doing so far, and then go back and refine it some more so that it matches almost exactly to the original structure. Okay, let's hide surface. What is going on here? Yep, as expected, this was a problem amino acid. Let's orient. This was a problem amino acid that we were just adding randomly. Oh, their published structure just decides not to include it. Okay, I can do that. They just decide not to include it. Okay. I can also do that. What else was there? Where's the lysine? Yeah, this lysine, which they did decide to include because you could actually see what's going on. This one they did decide to include. And hey, it matches almost exactly with what we had. Just a slight difference. A tiny difference. But yeah, so on the macro level, the idea is if you can't actually distinguish what's going on in there, you don't have to include it, which makes sense. And by doing this exercise, or by building and refining your model in PHENIX.refine and Coot and going back and forth, PHENIX.refine and Coot, and then checking yourself against the original structure, you are able to go in, see how you're doing, see what the standard is, and then match with what you're doing with the standard. That is one of the ways you can go from no structure to structure to initial refinement to manual refinement, and then cycle through initial refinement, manual refinement until you have a good enough structure that you then compare to the original structure to double check, see how you're doing, and then if you need to go back to refine Coot again, to ultimately give you a better picture and improve your skills on how to refine the structures for the determination development of ultimately